pi over 6. 1, 2, 3, 1 at pi over 6. Yes, that's true. So if I was to do trig inverse, aka take sine inverse of both sides, sine inverse of sine cancels out, x is equal to, sine inverse of 1/2 will be pi over 6, but pause. Sine inverse is understood to only be looking at what angle? Actually, no, sine is closed. Tangent is open. Do you guys remember what angles sine inverse looks at? Negative pi over 2 to pi over 2. So we're only allowed to look first and fourth quadrants. First quadrant, sine is positive at pi over 6. One answer. Done. But wait a minute, down here, oh, did I accidentally erase it without meaning to? Down here, it tells me don't just do the trig inverse. Look at all possible angles within negative pi to pi. So negative pi in the third and fourth quadrants, and I'm looking at 180. We already said pi over 6. You guys are totally right. That's right here. But don't we know that sine hits a positive number twice in the unit circle? Where else is sine positive? 5 pi over 6. Does that fit in my going up to pi? Yeah. So I'm going to have x is equal to not just pi over 6, but 5 pi over 6. Even though we think of an inverse trig to get to x, sine inverse and sine inverse, even though we have to use that, sine inverse would only give me 1. But when it asks me for more, or a range of angles, I take the sine inverse, pi over 6, and I use it and my knowledge of the unit circle to find however many answers they say they want. Or I should say, all the correct answers in whatever interval they give. Now, what if they had just given 0 to negative pi, or I should say negative pi to 0? Would I have any answers? No, it's not possible in that range, in that interval, but it was possible going up to pi. Now, what's the difference in this wording? This one gave us an interval, so we kept on going and found more than one. This one was just trig inverse, so we only found the one principal value that was allowed. This one uses the word, ooh. But wait a minute. All angles means coterminals. How many times can you go around a Ferris wheel? Don't answer that as far as practically speaking, but can't the Ferris wheel keep going and going and going? Isn't it going to keep on passing? What if they change the ride to go the other direction? Keep going and going and going? Well, stink. We know the two different places in the unit circle, but if they want all, we're going to use those two different places and say, hey, wait, all those coterminals can be two. I can't say all angles because it's only two locations, but those two locations can be passed again and again and again and again. With 0 2 pi's or 1 2 pi or 3 2 pi, 1 revolution, 2 revolutions, 3 revolutions, or negative 1, negative 2, negative 3. I don't even need to say more than that. All I need to say is, okay, the two locations and their coterminals, and we show that with plus 2 pi n plus 2 pi n. And if we were in degrees, we wouldn't do and 2 pi n, we'd do and 360 n. The n says, yeah, sure, multiples, positives, negatives, I don't mind, but revolutions plus all the possible revolutions. Do you guys see the difference in the answers for a very similar question? Actually, the question is the same. The directions are different. Does that make sense? Inverse, give me 1. All the angles within, keep looking for any more that possibly occur in those intervals. All, think about the locations and their coterminals. Yeah? So with trig inverse, we're going to think of one principal. Which one? Principal. One principal value, like the principal of the school. All the angles within, we're going to keep looking. We're going to get the 1, but we're going to keep looking for all the valid ones they want. And then plus the coterminals. And to get the coterminals, we're going to add 2 pi n. We're going to add 2 pi n. The only time it might get weird is if we have a tangent, because tangent happens in the first quadrant and in the third quadrant, which is just pi apart. So for tangent, we might just take 1 and add pi n, and we'll get to the second and the third and the fourth with one nice, pretty equation, but we'll see that when it comes up, which will probably not be today. Now, you don't need to write this down, okay? But they have given you some homework, especially when we were graphing trig functions, where they had you do something like graph this side and then graph that side and be like, hey, so when does this happen? And so one way of visualizing when sine is 1/2 is to think of the sinusoidal curve and put the 1/2 in between the 0 and 1 and be like, hey, it hits here and here and here and here and, well, et cetera, et cetera. So it's another way of thinking about how it's the first and second quadrants, not the third and fourth, because sine goes up and then down. Some of your brains, this might be helpful. Some of your brains, you're like, nah. I'm much more used to the quadrants and the unit circle. But both ways say pi over 6 and 5 pi over 6. Even though it's awkward, pi over 2, 1/3 of that, pi over 6, and 5 pi over 6. Both of them show the same intersection points or the same times. But what's the long story short? You need to know your unit circle backwards. So here's our steps for section 5.3. Somehow, regardless of the directions, if you're solving a trig equation, you got to get the trig alone. Somehow, you got to get the trig alone. If you can't get the trig alone, and I'm going to put a quick little, factors are okay. Because if we can get it factored, maybe there's more than one trig function. If there are factors, we can set each factor equal to 0. Factors are okay as long as we have factors equal to 0. If factors are equal to a number, we're in some big trouble. If we have factors equal to 0, we can set each factor equal to 0. Like you guys have done when you see something like x minus 2 times x minus 3 equals 0. Oh, x equals 2 and x equals 3. We don't mind factors. Factors are okay. But if we can't get the trig alone, and or we can't get it factored, we're going to have to use our transforming skills, which you used on verifying identities, to take something that looks like this. How do I solve that equal to a number? And get it to look like that. Oh, now I can set it equal to a number. Or look at number 30. What if you had this equal to 2? I don't know. Look at that. It's horrendous. That equal to 2. How do I get a trig alone? But what if you transform it to this equals 2? Oh, 1 over sine is equal to 2. Sine is equal to 1/2. I can do this where that is impossible. So you guys have been building skills, even in section 5.2, to say if you can make that look like this, an equation becomes possible. So guess what? 5.1, 5.2 skills are going to be used in big ways in section 5.3. For example, oh, does this need that much work? Solve for all solutions. All well and good, we're adding 2 pi n at the end, but we don't have to do a t-proof. It's not a verify. So what can we do? In section 5.3, conditional equations, we do whatever we can. It isn't always true. So we have to figure out, when is this true? Well, 2 cosine of x plus 1 is equal to 0. Isn't that when cosine of x is equal to negative 1/2? This is a super easy. Cosine equals negative 1/2. We're looking for all solutions, which means find the locations where this is true. Cosine is negative in the second quadrant and in the third quadrant at the pi over 3's. Isn't that 2 pi over 3's? And then 4 pi over 3? You guys need to know your unit circle? The answer is yes. Was that kind of basic? Oh, add, combine like terms, and then get cosine of x by itself. Yeah, is it going to get harder? But what if you make that 1 minus cosine squared? Then can you? Oh, everything comes together. Bye, cool kids. We're going to keep this up tomorrow. Some of you might want to start playing today. I'll see you guys later.
I love play a game with
It's playing, but playing still need to know the unit circle.